In this lesson, we want to review solving linear inequalities in one variable. So in the traditional sense, when we think about an inequality, we're thinking about a statement that two algebraic expressions are not equal in value. So something like 6 is less than 12 is a way to notate that 6 is a smaller number than 12. Or something like -4 is greater than -11 is a way to notate that -4 is larger, or you could say greater than -11. So when we work with inequalities, we have strict inequalities and we have non-strict inequalities. So strict inequalities, you have strictly less than and strictly greater than. With non-strict inequalities, which we'll see in a moment, you have less than or equal to, and then you have greater than or equal to, so you're allowing for the possibility of equality. So when we have an inequality with a variable involved, we need to understand interval notation, and we need to also understand how to graph an interval on the number line. So if we see something like x is greater than 5, how could we notate this on the number line? Well, first let's think about x equals 5. If x equals 5, then x can only be one value, it can only be 5. So on the number line, I could just put a dot there, right? A filled in circle, however you want to think about that. But if x is greater than 5, I don't want to go through and put a dot at every possibility, right? Because it's anything larger than 5. So it could be 6, it could be 7, it could be 8, it could be 9, it could be 2 million. So I want to basically shade all of these. And I would just shade the number line, and I would shade that arrow to say this continues forever. But I've got to have a point known as a boundary, okay? A boundary is what separates the solution region from the non-solution region. So over here, this is my solution region, okay? Anything on the right side of 5 satisfies this inequality. So if I took 6 and plugged it in, 6 is greater than 5, that's true. Okay, that's true. If I took 1 million and plugged it in, 1 million is greater than 5, that's true. Then anything on the left of 5 is in the non-solution region, right? Because it wouldn't work. If I took a 3, for example, and I plugged it in, is 3 greater than 5? No, this is false. Okay, this is false. So 5 itself is our boundary. It's where it separates the solution region from the non-solution region. So at that point, you either want to use a parenthesis or a bracket. You use a parenthesis when it's not included, and you use a bracket when it is included. Okay? So in this case, it's not included because we have a strict inequality. So what we want to do, we want to put a parenthesis facing in the direction of the solution region. So this is how you would graphically notate that x is greater than 5. 5 is not included, that's our boundary, but anything larger than 5 is included, and that's why it's shaded. Now, some of you will see a different notation. At 5, you may see an open circle to show that 5 is not included. So you might see something like this, and then everything is shaded to the right, and that's okay too. No problem there, it's just a different way to notate it. In this course, we're basically going to stick to this. So we're going to put our parenthesis here and then shade everything to the right. But feel free to do it either way. Now, you also need to think about interval notation. And it basically follows the same concept as we just looked at with graphing. So you're going to think about your smallest value. And you're going to think about your largest value. And you're going to separate them with a comma. Now, in this particular case, you don't really have a smallest value, right? Because if you think about it, 5 is your boundary, but anything larger than 5 works. So 5.00000001 works, or 5 point, you can extend a million zeros and then put a 1, that works. So for the smallest value, we just put 5, because that's as close as we can really get. And then we're going to put a parenthesis to the left of that to say that 5 is not included, right? So this just means not included. Not included. But we know automatically that anything larger than 5 would be included, okay? Then we put a comma, and then our largest value, again, because there is none, we use infinity. This is just a concept. So we put our infinity symbol to say this is going to continue forever in the right direction. You always use a parenthesis with infinity, okay? So again, not included. So 5 comma infinity with a parenthesis next to each. So this is graphically, and this is with interval notation. Now let's look at a less than. So x is less than -3. So again, x can be any value that's less than or to the left of negative 3. So negative 3 is my boundary. My solution region is to the left of negative 3, so I want to shade everything to the left of negative 3. So I'm going to shade this arrow and all of this to negative 3. And at my boundary, I'm just going to put a parenthesis facing to the left, okay, to show that negative 3 is not included. But again, because I've shaded to the left, everything that's less than negative 3 would be. In interval notation, it's the same concept. We're going to put a negative infinity here to represent our smallest value because there is none. I always use a parenthesis with either negative infinity or positive infinity. Then comma, I'm going to put negative 3 for my largest value. And again, because that's not actually my largest value, because it's not included, I'm going to put a parenthesis there. So you have negative infinity, you have negative 3, you have a parenthesis next to each. Let's quickly look at non-strict inequalities. So you have less than or equal to and greater than or equal to. So these allow for the possibility of equality. So x now is greater than or equal to 5. So it's basically the same thing, but we allow for 5 to be part of the solution. So I use a bracket when that occurs. So all I need to do here is just put a bracket at 5 and shade everything to the right. And the bracket just tells me that 5 is included. Now, in interval notation, I can put a bracket of 5, comma, infinity. And again, the bracket just says that 5 is included. Okay, it's part of the solution now. And it's worth noting here that we also have another notation that we can use for this. Some textbooks, when you have a non-strict inequality, will put a filled-in circle at the boundary. So to include 5, instead of using a bracket, they'll put a filled-in circle, okay? So the filled-in circle means it's included, and then we would shade everything to the right like this. But again, in this course, we're going to stick to using a bracket. So I'm going to put a bracket at 5 and just shade everything to the right. You can use any method you want. They're both the same, just different ways to show the same concept. Then for x is less than or equal to negative 3, again, I'm going to use a bracket because negative 3 is part of my solution. So I'm going to put a bracket at negative 3 facing to the left and just shade everything to the left here. Okay. In interval notation, I've still got my negative infinity, and then comma, I'll have a negative 3 with a bracket next to it. So negative 3 is included, so that's why I have my bracket. With positive or negative infinity, I always use a parenthesis. All right, so now let's move into what a linear inequality in one variable is going to look like. So we have stuff like ax plus b is less than c, where a does not equal 0. So essentially here, this is generic. We have a, b, and c, which are any real number, with the exception that a cannot be 0. And we could basically replace this less than with a greater than, or a less than or equal to, or greater than or equal to. So something like 3x plus 5 is greater than 11, or something like negative 7x plus 2 is less than or equal to 16. So essentially exactly what we saw when we solved linear equations in one variable, with the exception of we're flipping the equality sign into an inequality sign. All right, so suppose we came across an inequality such as x minus 11 is less than negative 14. So before we solve this, let's think about an equation. So x minus 11 is equal to negative 14. How could we solve this? We know about the addition property of equality. That tells us we can add or subtract the same number to, or in the case of subtraction from, both sides of an equation and not change the solution. So to isolate x here, all I need to do is add 11 to both sides of the equation, right? Because I'm subtracting away 11 here. If I add 11, I'm going to basically cancel this with this, and I'm left with just x. So here I would have x is equal to negative 14 plus 11 is negative 3. So we can use the same process when we solve inequalities. So let's erase this, and let's write our problem down here. So we have x minus 11 is less than negative 14. So when it's used with inequalities, it's called the addition property of inequality. And essentially, this property allows us to add or subtract the same value to, or in the case of subtraction from, both sides of an inequality without changing the solution set. Okay? So I'm using the same technique here. I want to isolate x. And since I'm subtracting 11 away from x, I just add 11 to both sides of the inequality. And again, this cancels, and I get x is less than negative 3. Okay, very, very easy. So we would want to notate our solution, again, using interval notation and then graphically. So to notate this in interval notation, I know that I would put a parenthesis and a negative infinity, and then comma, I would have a negative 3 there. And again, because negative 3 is not included, I'd put a parenthesis. So graphically, I would find negative 3, so that's right here. I'd put my parenthesis in, and then I would just shade everything to the left. Okay, so all of this going to the left, including the arrow. All right, let's take a look at another one. So we have x plus 9 is greater than or equal to 15. So again, I want to get x by itself. I always want to isolate x on one side of the inequality. So to do that, I can just subtract 9 away from each side of the inequality. And this guy right here is going to cancel. I'll have x is greater than or equal to 15 minus 9 is 6. So again, I've got a greater than or equal to there, so I want to use a bracket. So let's find 6 on our number line. We want to put a bracket to show that it's included. And then we're going to shade everything to the right. That's our solution region, okay? In interval notation, I would put a bracket and then put a 6. This would be my smallest number. And then comma, you would have infinity. That would represent the largest number, right? There is none. This continues forever. So now let's talk a little bit about the multiplication property of inequality. So you know that we have a multiplication property of equality that we use with equations. So if I had something like 5x is equal to 15, we know we can multiply or divide both sides of an equation by the same non-zero number and not change the solution. So since 5 is multiplying x here, I can divide both sides of the equation by 5, and I get that x is equal to 3, right? Very easy. You have the same property with inequalities, but you have an exception here that you really need to pay attention to. With the multiplication property of inequality, you can essentially multiply both sides of an inequality by the same positive number, okay, positive number, and not change the solution, okay? You can also divide both sides of an inequality by the same positive number and not change the solution. What about negative numbers? Well, we'll talk about that in a minute. So let's just look at this inequality real quick. So 5x is greater than 15. We know we want to isolate x. 5 is multiplying x, so we can go ahead and divide both sides of the inequality by 5, and we would get that x is greater than 3. In interval notation, we would put a parenthesis, a 3, and then we would have an infinity symbol and a parenthesis, okay? Graphically, I could put a parenthesis at 3 to show that it's not included. 3 is the boundary, and we're going to shade everything to the right. Let's take a look at another one. So now we have 7x is less than or equal to 49. So 7x is less than or equal to 49. Again, if I want to isolate x, I can just divide both sides of the inequality by 7. And I'll get x is less than or equal to 7. Okay, very, very easy. In interval notation, you would have a negative infinity, and you would have a 7 here. But again, because this is less than or equal to, next to the 7, I put a bracket, okay, because it's included. So graphically, I would look at 7, I would put a bracket, and then I would shade everything to the left here. This is my solution region. So all of this. All right, so let's talk about the case where you're multiplying or dividing an inequality by a negative number. So for this, I want to just show you real fast what happens when you multiply an inequality by a negative number. All right, so suppose we started out with something like 3 is less than 7. We know at this point that this is a true statement. 3 is less than 7. If I multiply both sides of this guy by positive 2, so let's say I multiply by 2 over here, and I multiply by 2 over here. So 2 times 3 is 6. 7 times 2 is 14. 6 is less than 14. That's still true. Okay, so nothing really changed there. I still have a true statement. But let's say I multiplied both sides by negative 2. What would happen? Well, I'd have negative 6 over here, and I would have negative 14 over here. Now this is false. Now this is false. So what happened here? Well, the smaller number, when it got multiplied by a negative, became a smaller negative, and therefore a larger number. The bigger number, when multiplied by a negative, became a bigger negative, and therefore a smaller number. Okay? A bigger negative represents a smaller number because it's further to the left in the number line. So when you multiply or divide an inequality by a negative, you've got to flip the direction of the inequality symbol. So to make this true, when we multiplied here, we had to flip this guy. So instead of a less than, it had to become a greater than, and then it becomes a true statement. Okay? So we want to keep this in mind when we solve something like this. So we have negative 9x is greater than or equal to 18. So negative 9x is greater than or equal to 18. Okay. So I know that x needs to be isolated by dividing both sides of the inequality by negative 9. What I've got to do is flip the direction of the inequality symbol. Right now I have a greater than or equal to. I want a less than or equal to. So negative 9 over negative 9 is 1. You just have x. So x is less than or equal to. 18 over negative 9 is negative 2. Okay? If you forget to flip the direction of the inequality symbol, you will absolutely get the wrong answer. Okay? So you've got to make sure if you're multiplying or dividing both sides of the inequality by a negative value, you flip the direction of the inequality symbol. Very important. So graphically, if x is less than or equal to negative 2 is the boundary. So I'm going to put a bracket at negative 2, and I'm going to shade everything to the left. In interval notation, I'd put negative infinity, comma negative 2. I'm putting a bracket next to negative 2 because it's included, and a parenthesis next to negative infinity. All right, let's take a look at another. So we have negative 1/3 x is less than 2. Again, negative 1/3 x is less than 2. How can I isolate x? Well, I need to multiply both sides by the reciprocal of negative 1/3. Basically, I need to multiply both sides of the inequality by negative 3. So times negative 3 and times negative 3. Now, I am multiplying both sides by a negative, so I've got to flip the direction of the inequality symbol. Right now it's a less than, it's going to become a greater than. I know this is going to cancel, and I'll just have x. And over here, 2 times negative 3 is negative 6. So we get that x is greater than negative 6. In interval notation, I would put a negative 6 next to a parenthesis, again, because it's not included. Then comma, you have the infinity symbol, because this continues forever in the right direction. And then a parenthesis next to that. So graphically, at negative 6, we'd put a parenthesis. And then we would just shade everything going to the right. Okay, again, including this arrow, because the solution region continues forever in the right direction. All right, so now let's talk about how to solve any linear inequality in one variable. You're going to follow, again, the same steps you used for an equation, with just a minor difference, the fact that if you multiply or divide by a negative, you need to flip the direction of the inequality symbol. So the first thing is to simplify each side separately. So combine like terms, clear any parentheses, do all the simplification you need to do. The next thing is to isolate the variable terms on one side and the constants on the other. So again, you can use the addition property of inequality to do that. Then you want to isolate the variable. So you're going to use your multiplication property of inequality to do that. And then lastly, you're going to check. But as I'm going to show you, when you check an inequality, it's much more tedious. Okay, there's a lot more involved than when you checked an equation. So for this one, you kind of put an asterisk next to it and say, if time permits. All right, let's take a look at an example. So we have 2x plus 9 times the quantity x minus 5 is less than 4 times the quantity 4x minus 15. So we have 2x plus 9 times the quantity x minus 5 is less than 4 times the quantity 4x minus 15. So what I want to do here is first simplify each side. So let's go ahead and do that. So over here I have my 2x, and then plus 9 times x is 9x, and then 9 times negative 5 is negative 45. This is less than 4 times 4x is 16x, and then 4 times negative 15 is minus 60. All right, 2x plus 9x is 11x, and then minus 45, and this is less than 16x minus 60. So now I've simplified each side as much as I can, and it's time to move all the variable terms to one side, all the numbers to the other. So I'm going to subtract 16x away from each side of the inequality. So that's going to cancel. I'm going to add 45 to each side of the inequality. That's going to cancel. 11x minus 16x is negative 5x, and this is less than negative 60 plus 45 is negative 15. Okay, so what I want to do now is divide both sides of the inequality by negative 5. But again, because I'm dividing by a negative, I've got to flip the direction of the inequality symbol. Right now it's a less than, it's going to become a greater than. So this becomes x is greater than negative 15 over negative 5 is going to be positive 3. So x is greater than 3. So let me erase all this. And so x is greater than 3. Okay, so in interval notation, we know this would be a parenthesis, a 3, and then an infinity here, and a parenthesis. Graphically, I would put a parenthesis at 3, and then again, I would shade everything to the right. Now, I want to teach you how to check this guy, okay? I'm not going to check anything after this one because it's just so tedious. But essentially what you want to do is replace your inequality symbol in both the original inequality and your solution with an equals. So I would erase this and put equals, and I would check x equals 3. This is my boundary. Again, we talked about the concept of a boundary. It comes up all the time when you work with inequalities. It separates the solution region from the non-solution region. So you can see at 3 here, if I just circle it, everything to the right of 3 is in the solution region and satisfies the inequality. Everything to the left of 3 is in the non-solution region. 3 is included for a non-strict inequality, but not included for a strict inequality. So in other words, if I change this to a less than or equal to, this would become a greater than or equal to, and this guy would be included. I'd have a bracket there. But because we had a strict inequality there, it's not included, and so it's part of the non-solution region. Okay, but it's still considered the boundary because it separates the two. We check our boundary. So essentially I plug a 3 in for each occurrence of x. So I'd plug a 3 in here, and I'd plug a 3 in here, and I'd plug a 3 in here. And I'm looking to see if I get a true statement. So 2 times 3 is 6, plus 3 minus 5 is negative 2. 9 times negative 2 is going to be negative 18. So I can put 6 minus 18. This should be equal to 4 times 3 is 12. 12 minus 15 is negative 3. You would have 4 times negative 3. So 4 times negative 3 is negative 12. 6 minus 18 is negative 12. So you're good to go here. Okay, so the boundary is good. So now what I want to do is I want to grab a number that's in the solution region, and I want to check that. So this is a less than. So if I check something in the solution region, it should result in a true statement. So let's just grab 5. So we'll plug a 5 in here, and here, and here. So 2 times 5 is 10, plus 5 minus 5 is 0. 0 times 9 is 0. So you just have 10 over here. So this is less than. 4 times 5 is 20. 20 minus 15 is 5. And then 5 times 4 is 20. So is 10 less than 20? Yes, this is true. So you're good to go there. Then you want to check something on the other side of the boundary, so something in the non-solution region. Let's just choose 0 because it's easy to work with. So we'll plug a 0 in there, and also here. Okay. All right, so 2 times 0 is 0, so that's gone. 0 minus 5 is negative 5. 9 times negative 5 is negative 45. So this is less than. 4 times 0 is 0. 0 minus 15 is negative 15. 4 times negative 15 is negative 60. So is negative 45 less than negative 60? No, it isn't, right? Negative 45 is a smaller negative and therefore a larger number, so this is false, okay? And that's good because we picked a number in the non-solution region. It should not work. So we verified that our solution here, which is x is greater than 3, is correct. All right, let's take a look at another one. So we have negative 5 times the quantity 5x minus 11 minus 9 is greater than or equal to 7 times the quantity 9x minus 6. So again, I'm going to start by simplifying each side. So negative 5 times 5x is negative 25x. Then negative 5 times negative 11 is plus 55. Then minus 9, and this is greater than or equal to 7 times 9x is 63x. And then minus 7 times 6 is 42. So on the left side, 55 minus 9 is 46. So I can say this is negative 25x plus 46. This is greater than or equal to, we have 63x minus 42. Scroll down, get some room going. Now I just want to get all the variable terms to one side, all the numbers to the other. So let's subtract 46 away from each side. And let's go ahead and subtract 63x from each side. So this is going to cancel, and this is going to cancel. Negative 25x minus 63x is negative 88x. This is greater than or equal to negative 42 minus 46. is negative 88. Okay? So to get x by itself, we divide both sides of the inequality by negative 88. And this guy's going to flip because I divided by a negative. So you get x is less than or equal to 1. Okay, x is less than or equal to 1. So let's erase all this. So x is less than or equal to 1. If x is less than or equal to 1, then at 1, I'd put a bracket, and then I would shade everything to the left. And then in interval notation, I would have a negative infinity, and then comma, I would have a 1, and then just make sure you put a bracket there because 1 is included. Let's take a look at another one. So we have negative 3 times the quantity 3x plus 1, and then is greater than negative 2x plus 3 times the quantity x minus 2. So again, I'm going to simplify each side to start. Negative 3 times 3x is negative 9x, and then negative 3 times 1 is minus 3. This is greater than, you have negative 2x, and then plus, you have 3 times x, which is 3x, and then minus 3 times 2 is 6. So on the right side here, negative 2x plus 3x is just x. So we'll just put x minus 6 like that. Now I'm going to get all the variable terms to one side and all the numbers to the other. So I'm going to subtract x away from each side of the inequality. I'm going to add 3 to each side of the inequality. And this guy's going to cancel, and this guy's going to cancel. So negative 9x minus x is negative 10x. And this is greater than negative 6 plus 3 is going to be negative 3. So to finish this up, let me kind of erase this. To finish this up, I'm just going to divide both sides of the inequality by negative 10. And again, I've got to flip the direction of the inequality symbol. So negative 10 over negative 10 is obviously 1. So you have x is less than. You have negative 3 over negative 10, which is just 3/10. So in interval notation, I'll have my negative infinity, and then I'll have 3/10. And then again, I've got to use a parenthesis next to 3/10 because it's not included. So graphically, we have this in a scale that represents the integers. 3 divided by 10 is 0.3. So let's just say it's about right here. I'm just going to write a little marking there and say this is 3/10. And in other words, I would just go ahead and put a parenthesis there and just shade everything to the left. Okay. If you're working with a pre-drawn graph like that, just find out an area that makes sense, put a little marking and notate it. In this case, we're just notating it to say we have 3/10. And we just draw a little arrow going there to say, hey, this is 3/10. Put your parenthesis in this case because it's not included, and then just shade everything to the left. All right, for the last one, we'll look at one with some fractions involved. So we have 4/3 times the quantity x plus 5/2 is greater than or equal to, you have negative 2 times the quantity negative 4x over 3 plus 5/3. So if you want to clear the fractions, let's go ahead and clear the parentheses first. So 4/3 times x is just 4/3 x. Then plus 4/3 times 5/2 would be 20 over 6. This is greater than or equal to negative 2 times negative 4/3 x would be positive 8/3 x. Then negative 2 times 5/3 would be minus 10/3. Okay? So to clear the fractions, I'd multiply both sides of the inequality by the LCD. Okay? And what's that going to be? You have a 3, a 6, a 3, and a 3. So I'll put a 6 here and here. And let me kind of scooch this down. So 6 times 4/3 x. Think about 6 divided by 3 is 2. 2 times 4 is 8. So this would be 8x. Then plus 6 times 20 over 6. The 6's would cancel. You just have 20. Then you would have a greater than or equal to 6 times 8/3 x. 6 would cancel with 3 and give me 2. 2 times 8 is 16. So this is 16x. And then minus 6 times 10/3. 6 would cancel with 3 and give me 2. 2 times 10 is 20. So let's move all the numbers to one side and all the variable terms to the other. So I'm going to subtract 20 away from each side of the inequality. And I'm going to subtract 16x away from each side of the inequality. So this is going to cancel, and this is going to cancel. 8x minus 16x is going to give me negative 8x. This is greater than or equal to negative 20 minus 20 is negative 40. So very easy at this point. We divide both sides of the inequality by negative 8. And again, we're dividing by a negative, so we've got to flip the direction of the inequality symbol. This will be a less than or equal to now. So you get x is less than or equal to negative 40 over negative 8 is 5. So let's erase everything. So again, x is less than or equal to 5. So in interval notation, we know that would be, we have a negative infinity here on the left, and then we have a 5 on the right with a bracket next to it, okay, because 5 is included. Find 5 on the number line, and we're going to put a bracket there, and we're going to shade everything to the left, our solution region.